Okay. Hello, everyone. I'm Peter Burton. This is the first recorded lecture for our probability course. Uh, so, in this recorded lectures, we're going to introduce new material, and then these recorded lectures will be on Wednesday and Friday, and then we'll have the interactive lectures on Mondays. So this will be the first lecture of new material. The first topic we want to discuss is just to set some notations that we're going to use going forward. So the first notations we want to introduce are notations for uh, fundamental sets of numbers. So the first set of numbers we want to think about are the natural numbers, and we represent them with this blackboard bold N. Okay, so these curly braces are supposed to delimit a set, and then we have this set of natural numbers, which are the positive whole numbers. And we call them natural because they come to us as children, synonymous. They come to us as children, and they're synonymous with the concept of counting. So, in theoretical math, we usually start counting from one, just like in the rest of the world. In computer science, sometimes they start counting from zero, and in that case, sometimes people would include zero as a natural number. It's just a superficial convention whether you start from counting from zero or one. And so it's just a superficial convention whether zero is included as a natural number. We're going to adopt the convention that zero is not a natural number and the natural numbers start from one. So the next notation we want to introduce is the blackboard bold Z. Okay, so the integers are the full set of whole numbers, positive and negative. Just what you get by adding zero or by including zero and the negatives of natural numbers. And we have this blackboard bold Q. Is the set of rational numbers. So we want to put this curly brace to delimit a set, and then we're going to say that the rational numbers are all numbers k over n, where k and n are integers, and n is not zero. So we stipulate that k over n equals m over L if KL equals MN. So the rational numbers are the collection of all integer fractions, and we have this stipulation that certain integer fractions are equal to each other to reflect the concept of canceling out a common factor between the numerator and denominator. So we can say like 3 over 6 is the same thing as 4 over 8. Because 3 times 8 is 6 times 4. So rational numbers are a little bit more complicated than integers because they have this subtlety with superficially different rational numbers reducing to the same thing in lowest terms, but they're still defined in a very concrete way as ratios of integers. So the last notation we want to introduce is this blackboard bold R. So this blackboard bold R is supposed to be the set of real numbers. So informally, you can think about the set of real numbers as the collection of all infinite decimals. So, some decimals are repeating and some decimals are non-repeating, and it ends up that repeating decimals correspond to rational numbers and other decimals which don't repeat correspond to what we call irrational numbers that fill in the holes between rational numbers to produce a continuous line. So real numbers include things like the square root of 2. So the square root of 2 is roughly, 1.4142, and it keeps going, but it's an infinite non-repeating decimal. And we also have things like pi. So, in this course, we won't give an explicit construction or a careful logical analysis of the real numbers. So, to understand the theoretical underpinnings of real numbers, you need to take a course in real analysis, which I think is Math 361K. But what we're going to do in this course is work with real numbers on a semi-intuitive level where we just treat them as you're used to in elementary calculus, and where we write things like the square root of 2 and pi, or we can say if x and y are real numbers. So this symbol here, oops, I wanted a highlighter, not an eraser. This symbol here is what we call the element symbol, and it means the things on the left are an element of the set on the right. So if we're dealing with real numbers, we can say something like so we can just work with real numbers as we're used to, with variables like x and y, or explicit things like square root of 2 and pi. And even though we haven't really probed their logical innards, we're going to assume we have a familiarity working with real numbers. So these four symbols, the blackboard bold N for the natural numbers, the blackboard bold Z for the integers, the blackboard bold Q for the rational numbers, and the bold R for the real numbers, are the most hardwired symbols in math. You'll never ever see these symbols used for any purpose other than what I have written here. Okay. So I want that to be landscape. Let's see. Okay. So the next kinds of notation we're going to use are sums and products. So you may have seen these notations before, but I just want to clarify them now at the beginning of the course so everyone's on the same page. So we can say if A1 up to AN is a list of n real numbers, then we write sum k equals 1 to n ak for the sum a1 plus a2 up to plus an. So this sigma notation for sums is a more efficient and controlled way of expressing sums of indeterminate length than the notation I have on the right of the second line with the ellipsis. So if you think about this list of n real numbers, it's pretty intuitive what the notation with the ellipsis is supposed to suggest. You're just adding up this list of numbers. And then when we have the sigma notation, it's doing the same thing. It's representing the purpose of adding this list of numbers, but the notation where we have this k as a counter variable is going to allow us to manipulate sums in a much more sophisticated way than if we tried to carry on with ellipses everywhere. So in the sum, there's a number of variables. There's the a, which represents the name of the things in the list, and there's the n, which represents the length of the list, but I really want to focus on these two variables k that appear at the bottom of the sum and in the subscript to the right, because this variable k is a dummy variable or an in-text variable, which is working like a counter for a loop. It has no meaning outside of how it's bound up in the sum, and you can't use the variable k for any other purpose when you're using it to count or index the terms like this. So it would be really identical if I chose to write an expression like this. So if instead of sum k equals 1 to n at k, I wrote some j equals 1 to n aj, these two expressions would be logically identical. It's just that I've changed the letter I'm using to index my sum, but that letter is only serving this index purpose, and changing it doesn't do anything other than superficially change the way the notation looks. So, we can see an example. So we can see that if we have sum k equals 1 to 4 of 3k. So to evaluate this sum, we plug in 4 different values of k corresponding to 1 through 4. So this is 3 plus 3 times 2 plus 3 times 3 plus 3 times 2. Or, sorry. Plus 3 times 4, which is 30. Okay, so we have a similar notation where we write this capital pi, so the product from k equals 1 to n of ak for the product a1 times a2 up to an. So the role of the index or counter variable here is exactly the same as for the sum. And we can see, for example, if we have the product from k equals 1 to 4 of 3k. So this is 3 times 6 times 9 times 12, which is 1944. Reminds me of, it's funny, when you have a number like 1944, it makes you think of a year, but it's not clear at what point you stop thinking about numbers as numbers and start thinking about them as years. But anyways, luckily it's not 1944 anymore. So this is just what we're going to use as notations for sums and products. Okay, so now we're going to introduce the first concept, which is kind of specific to the course material as opposed to just generalized mathematical notation. So this is what I'm gonna call the principle of successive experiments. So this is an extremely fundamental idea in mathematics, which is unfortunately so basic that nobody ever thought to give it a really explicit name that you can just use to refer to it. So I'm going to call it the principle of successive experiments. I think your textbook might, or the textbook might call it something like the basic principle of counting, but that's really vague. So I'm going to call it the principle of successive experiments. So here, what are we trying to say? So we're trying to say if experiment 1 has n possible outcomes, and experiment 2 has m possible outcomes, then if we perform experiment 1, followed by experiment 2, there are n times m possible outcomes for the combined experiment. Okay, so more generally, if we have a list of t experiments, and for k between 1 and t. So here again, I'm using the element symbol to say that k is an element of the set of numbers between 1 and t. And then we're going to say, okay, so we have another variable. Let's call it jk. Outcomes for experiment k. There are product k equals 1 to t, jk outcomes for the full combination of t experiments. Okay, so the idea is that, well, if you have an sequence of experiments and you're trying to figure out how the numbers of outcomes for the individual experiments are supposed to combine to tell you the number of outcomes for the total experiment, what you need to do is you need to multiply together the number of outcomes for each of the individual experiments. So in the first example, where there's only 2 experiments, we're using the variables n and m for these 2 numbers, which are the 2 numbers of possible outcomes. And then in the second paragraph here, we're generalizing this concept. So if you set t equal to 2 in the second paragraph, you get an assertion which differs from the first paragraph only in notation and phrasing. If you set t equal to 2 in the second paragraph, its logical content is exactly the same as the first paragraph. Okay, so we can see an example. Okay, so let's say we have a committee with 5 doctors, 4 lawyers, and 5 mathematicians. So a subcommittee with 1 member from each group is to be chosen. And we want to know how many committees are possible. Okay, so we need to think of this in terms of our principle of successive experiments. So we can think, okay, so experiment 1. So what do we do in experiment 1? In experiment 1, we pick 1 out of 5 doctors. So in experiment 2, pick 1 of 4 lawyers. And experiment 3, pick 1 of 5 mathematicians. Okay, so we have these 3 experiments, and the first one has 5 possible outcomes, so the second one has 4 outcomes, and the third one has 5 outcomes. So we do the total is just 5 times 4 times 5, which gives us 100. Okay, so this is an example of how to apply the principle of successive experiments, where the experiments are very simple and just involve picking one from a group of a specified size. Okay, so now we want to apply the basic principle of successive experiments to a particular situation, which is really central to probability theory. And this is the question of arranging distinct objects in a line. So let's say how many ways are there to arrange n distinct objects in a line? Okay, so let's think about how we're doing it. Let's think about these objects as really being physically represented by little spheres with numbers on them. So we have all these little spheres with numbers on them, and we're thinking that there's an indeterminate total of n spheres that we're trying to arrange in a line. So we have this, let's think of them as little slots, and when we're arranging these spheres in a line, what we're doing them is putting them in these slots. Okay, so the way we want to do this is we want to think of it again in terms of successive experiments. Okay, so when we have experiment 1 and we fill the first slot, we have n spheres to choose from. We can pick any of the n spheres on the left and put it in the first slot. So experiment 2, we're thinking of as filling the second slot. So when we fill the second slot, we have n minus 1 spheres to choose from, because we have removed one of our choices by putting it in the first slot. So now we have n minus 1 spheres to choose. Okay, so we can see we can keep going down like this, and if we see what's going to happen is that the total is going to be n times n minus 1. So that's the first two experiments. Then the third experiment, we're going to have n minus 2 choices. And then we're going to finally, in the slot here, which is third from the last, we're going to have 3 choices left. So we're going to end up with 3 choices for the third last and 2 choices for the second last. And then in the very last stage, we're going to have only 1 choice. And so this expression, which is the product of all the numbers between 1 and n, is a very important quantity. It's called n factorial. So n factorial is the number of ways to arrange n distinct objects in a line. And what we've done here is to give a derivation of that from the principle of successive experiments. And so a way of arranging n distinct objects in a line is called a permutation. So what we're doing here in more formal language would be saying we're permutations of n objects. So a permutation is a way of arranging these objects in a line, and what we can see here is that through the principle of successive experiments, we've figured out that there are n factorial ways of arranging these things in a line. Okay, so we can see an example of how we can use this. Okay. Okay, so what can we do? Well, let's say that we consider a class with 6 math majors and 4 physics majors. So if the math majors are ranked within themselves, and the physics majors are ranked within themselves, how many rankings are possible. Okay, so we can solve this problem by combining the principle of successive experiments with what we learned about factorials. So, for the math ranking, we're basically trying to arrange 6 people in a line. So we have 6 factorial, which is 720 ways. Okay, and then for the physics ranking, we have 4 factorial, which is 24 ways. So total should be 6 factorial times 4 factorial, which is 720 times 24, which gives us 17,280. So again, it's funny, 17,280 goes back to looking like a number again. It's too big to look like a year, at least in the present. Okay, so this is combining the principle of successive experiment with the calculation of rankings in terms of factorials. Okay, so the next thing we want to understand is how to arrange things in a line where some of them are alike. So suppose we want to arrange 3 red balls, 3 green balls, and 4 yellow balls in a line. So how are we going to count the number of ways of doing it? Well, what we're going to do is we're going to bootstrap ourselves from our understanding of factorials. So what we're going to do is we're going to say, first, assign a unique label to each ball. And consider the 10 factorial ways, so 10 factorial ways of arranging. Okay, so this doesn't solve our problem because we've introduced this kind of fictional additional data which doesn't appear in the question, specifically the unique labels for all of these balls. But now that we have unique labels, we can say, all right, I already know that there's 10 factorial ways of arranging with these unique labels. And then when we erase labels on green, we collapse all of the 3 factorial distinct green. We collapse all of the 3 factorial distinct arrangements of labeled green balls to a single arrangement. So what we're going to need to do is we're going to need to take these 10 factorial ways of arranging the distinct objects and compensate for the alike patterns by dividing the number of distinct arrangements that get erased when we put these things together in the context of the problem rather than the artificial context we introduced to help ourselves. So we got this 10 factorial by artificially labeling the balls, and then we're getting ourselves back to the situation that was described in the question by compensating for the lack of distinction by dividing the number of arrangements that artificially appeared due to that distinction. So this comes out to be 4,200. Okay, so we can formalize what we did there. So what did we do there? We can say if M1 plus M2 plus mk equals n, and n objects are divided into alike, so into k alike groups of size m1 up to mk, then there are n factorial divided by the product from k equals 1, or sorry, got to use a different letter there so I don't conflict. So j equals 1 to k of mk factorial ways to arrange in a line. Okay, and so this number is called the multinomial coefficient, n choose m1 through mk. So this is called the multinomial coefficient. Okay, so an important special case of the multinomial coefficient is if k equals 2, we write just n choose m instead of n choose m comma n minus m. So this is n factorial over m factorial times n minus m factorial. And this is what's called a binomial coefficient. Okay, so I'll end this first recorded lecture here.